Hello everyone, this is Mohsen Saraj from Ozen Engineering. I'm a senior application engineer for Ansys Safety. In this video, I want to talk about how to model open channel flow in Ansys Fluent by volume of fluid method. In the second part, I want to show you how to model the open channel flow when we have a deep more depth of the water. As you can see that we have two channels, a little bit changes into the geometry. They are joining together in this part, and here we can see that we have more depth for the water. Again, these are trapezoidal channels that we use this cross section. Regarding to the boundary conditions, similar for the similar inlets, outlets, the top surfaces open to the air and the walls. So almost simple, close geometry to the previous part, and we just want to see that when we have more depth into the into the channel, open channel, what we can see. Let's see what's happened. After creating the model in Ansys Discovery and meshing that in Fluent meshing, the model is transferred to Ansys Fluent. In Fluent, we at the very beginning at the general gravity activated, and we will run the transient simulation. For the modeling, multiphase volume of fluid method is chosen, and I also activated the open channel flow and also included implicit body force. By default, we have two phases for volume of fluid method. That here we have water and air. Primary phases is usually air because it has less density, and secondary phases is water, that we choose it water here. And to define water liquid, if we come here to the material for the fluid, usually we have only air by default given, but we can define a new model, like new material from the Ansys database here, that you can see. For example, I can choose the water liquid and with the given properties, or I can change it if I want. If I copy that, the water will be included into the model. I already did that, so that's why air and water liquid is included. So secondary phases in volume of fluid will be water liquid. We have to also set up the phase interaction, the interaction between air and water. Surface tension included with 0.72 Newton per meter, and we use continuum surface first for the modeling. So model, phases, and phase interactions, these are the 3 steps to set up the volume of fluid method. By default, k omega is k omega SST. K omega is already selected for by default by Ansys Fluent. I can change it to k omega if I want. Okay, to see that what options of if I want RNG or realizable. I just keep it as is, because here our main purpose of this video is to show that I have to use volume of fluid method. No temperature or heat transfer temperature here, so we don't activate the energy equation. So this is the important things for the models. And after that, for boundary conditions, inlet, these are the inlet already chosen. Okay, I choose pressure inlet, and for the pressure inlet, for the momentum, I just keep it as is. For multiphase, I activated open channel here. So I need to define the where the water is at the inlet, and what is the velocity, and where is the bottom of the channel. So these are the free surface level. It is what I choose. It is 10 centimeter. Previously it was on the first part on the 30 centimeter, so it is much deeper. More depth of the water we have, same velocity, and this is 0 for bottom level. It is given from the obtained from the geometry. So this is for the inlets. For outlet, I use pressure outlet. I just keep it as is. For the momentum, for multiphase, again I selected open channel, and again I have to set it in and tell the Fluent where the free surface is and where is the bottom level. Previously it was 0, but if you see that, as you can see that because of more depth that I wanted, this bottom here, okay, it is this one, it is for the it is this part, it is at the level of minus 10 centimeter below the XZ plane. So I choose it -1 here. Okay, we don't want this here for now. So and top faces opened. I just leave it as is, and I can set it open channel or not, but we really don't need that, okay, because these are open to the air. And I just leave it 0 gauge pressure. This is for the these are walls, and this is the interior. So after setting the boundary conditions, I can go and check the methods. I use piezo for the coupling of the pressure and velocity, and presto must be used for volume of fluid method for the pressure discretization. Second order discretization usually chosen for the momentum and for the turbulence and other things. I just keep the contours, the residuals as is. For monitoring, if we want to see what we want to choose, okay, I can come here for the solution and define, okay, for example, volume average. Here say that, okay, volume average for the velocity, for example, to see that, and this is interior, and we choose velocity magnitude. So I can choose this, and I can add also know that what's going on at the outlet. Okay, for example, here at the outlet surface, this is area weighted average. I can set it to the pressure or to the temperature or velocity here, whatever. I choose the velocity here to know that what's going on here. And other things here, if within and during the solution, I can have this report to see that, if, for example, I can go here, for example, for the, if I want to know the uniformity index, this is something also, or vertex average, these are some things also we can work on that. different things that we can choose for the reporting during the solution. So these are for the mm, for the report definitions and monitors, and then I can go and initialize the model. Okay, the model is already initialized. It could be from the all zones together, or could be from inlet or whatever. After initializing, I use patching, and here I choose that where I have water into the domain before starting the solution. It is for the initial condition. Here, because we don't want to simulate the filling of the channels, we want to see that if we have continuous flow into the channels, these channels, and we see that the merging, mixing of these flows together, what's going on here mostly in this part. So I already defined a region that here by cell register I can define it, and the the dimensions for the x values, y values, and z values, I mean the coordinates for this domain, it is depend to the where I want water into the system, and what are the dimensions that we can give taken from the geometry. So I already defined that. As you see that I said that from y value here, okay, y value here from minus 0.01 to plus 0.01 we have water. So it means that if I say that patching, I already did that. Okay, I have water included into the uh, these channels, small channels, and also to in this one. So I have leveled of the water at the free surface at 0.01, 10 centimeter. So we already done all of this. Before running, I can choose that to save it after a specific time steps or iteration or one. Also, I can define the animation if I want. I use isosurface to define where the free surface is. So I call it free surface. It could be in terms of different things, pressure, velocity, or whatever. I use it from phases, volume of fraction for the phases, okay, and also uh, and I define VOF equal 0.05 as where the free surface is. So 50. So the cells that includes both water and air. So I based on this isosurface, okay, I already defined some of the contours, for example for the velocity over the free surface. So as you see that I choose free surface and the walls and the velocity magnitude. It could be contour for the VOF as well, again where for example at the inlet, from inlet to outlet, and in this part it depends to the what we want to measure and what we want to see in that. I use these contours to define the animation, okay, to define the animation here, that we have these animations that you can see that, for example, uh, animation 1 use contour 1, animation 2 use another contour, and so on. And in each animation I can say that what is the increment to recording the results. I said that every five time steps. So suppose that everything's set it up, I can go for the solution, Again, I use 5 millisecond for the time step, and you can start with 200, 500, 1000, whatever number of time steps you want, and hit the solution. And I just set uh, 20 iteration for each time step. If I hit calculation, the calculation start. It will take time. Okay, so I back to you after the solution is done. I stop the solution after more than 10,000 time steps. Let's check the results here. For example, for animation, if we check the playback, some of the animations, let's just play that. This is for the animation of the as you see that the velocity of the free surface and in the channel. Let's play that for the velocity magnet. As you see that flow coming from these two and mixing here, merging together, but as you see and then the flow merging, mixing here, getting over there, and we see this traveling flow against uh, the direction of mainstreams, and even is affected the velocity inside each of these channels. Okay, yeah, I just play it one more time. Let's just a little bit slow it down. Here we see the mixing and merging of the water to incoming mainstreams from these two channels, and have the flow here affected. As you see, the velocity goes up to 1.78 whatever, and then now in these two channels we have like a kind of backward waves traveling toward the inlet. This is interesting. It also depends to the what is the velocity and the inlet boundary conditions. The velocity here, and you see the lower velocity toward the inlet after the merging, and coming back the waves, as you see that moving on the sides of the channel, moving toward the smaller channels. This is interesting. You can see this. They're getting close to this merging region of the when these two fellows mixing here. Getting to this merging point, and you see that now the backward velocity toward the inlets. You can see that. Okay, this is for top view. Of the velocity magnitudes at the free surface, and you see again the velocity at these two, this side and this side, the velocity of the waves coming back. One more time, play. This is interesting. Okay, we can have more animations here. Besides animation, we can check the visually we can see that what's going on for the pressure here. For example, I can choose where I can see the pressure. Minimum at the top, that we see that open to the air, and at the bottom higher pressure. We know about this. If you want to see the free surface, let's just here. Yeah, you can see that even at the main channel we can see the higher pressure there. I can see also turbulence. If for example I want to see here what's going on, very low high intensity for the turbulent kinetic energy, for intensity also as well. Yeah, you can see that because we have here the merging of this interaction between these two fluids together. Okay, also for the results we can check other things. For example, for the vectors, I define vector in terms of the z component. Z is in line these two channels, okay, from inlet to the outlet. So positive means that the flow coming back from outlet to the inlet, but incoming flow to the inlet is in the negative direction of the z direction. So here let me show you. Yeah, negatives means that the velocity start from inlet going this way, and in this one and going from inlet toward the outlet. Negatives. Magnitudes for the z component of the velocity. Positive means that no, the flow is coming back. So from outlet toward the inlet, toward the merging point, and in these branches toward the inlet. So yellow, as red and yellow, they are mostly positive. So in positive direction it means that from outlet to inlet, and the uh, blue and greenish, they are mostly the negative ones. So as you see that at the inlets we see negative, okay, and when here you can see the the flow that it is recirculate. Here you can see exactly mixing of these two main streams. At the sides that we see in the animations that the waves traveling backward, you can see this by positive. This arrow heads towards the positive velocity for z component of the velocity, and here these are negative, so it means that after the merging these two fellows push the fellow going toward the outlet. So it is good illustration and visualization of what's going on here. Okay, and it is interesting that we have this kind of ways to seeing the results. So different things that we can see, that hopefully by this video you have a just good overview to have to set up the model and use VOF method for open channel, have to set up the open channel model in Ansys Fluent, and have to see some kind of results like a flow mixing, like a pressure profiles, velocity profiles, turbulence intensity, and other things that we can have. Thank you very much. Thank you.